There's a cast iron skillet in your kitchen cabinet, or a hand plane on your workbench, or a set of old chisels in the back of your garage that is covered in rust. Not surface rust, the kind you can wipe off with an oily rag, but deep, encrusted, decades-old rust that has turned the metal the color of dried blood and eaten so far into the surface that every wire brush and sanding disc you have tried has either made no impression or scratched the base metal worse than the rust itself. You looked up what it would cost to have a professional restore it. You found out what a replacement would cost. And you made the quiet decision that the tool was probably not worth saving. It is worth saving. And the process that will save it costs less than $1 in electricity, uses materials you already own or can buy for $2 at any grocery store, requires no scrubbing, no sanding, no chemicals that will harm you or the metal, and works while you sleep. You set it up in the evening. You come back in the morning. The rust is gone. Not reduced, not loosened. Gone. Converted back into clean iron by the same electrochemical process that deposited it in the first place, running in reverse. The process is called electrolytic rust removal. It has been understood since Michael Faraday described the principles of electrolysis in 1833. It has been used by museum conservators to restore irreplaceable iron and steel artifacts for over 100 years. It is the standard method for cleaning archaeological iron recovered from shipwrecks, excavation sites, and underwater deposits where conventional abrasive methods would destroy the artifact along with the corrosion. And it has been entirely absent from every tool care guide, every restoration manual sold at hardware stores, and every product recommendation from the tool industry for the entire time that replacement sales have been more profitable than restoration knowledge. The tool industry in the United States generates over $40 billion in annual revenue. A significant portion of that comes not from first-time buyers, but from people replacing tools they already own. Tools that rusted in a garage, tools that were inherited and found corroded, tools bought at an estate sale for a fraction of their value precisely because the buyer did not know how to restore them. Every rusty tool that gets thrown away and replaced is a sale. Every rusty tool that gets restored is a sale that never happens. The industry's motivation to keep electrolytic rust removal out of mainstream consumer awareness is not complicated. It is just math. Welcome to $1 Miracle. This is where we open the vaults the tool industry hoped you would never find. If this kind of knowledge matters to you, subscribe now and hit the bell, because what I am about to show you will permanently change how you look at every piece of rusted metal you have ever considered throwing away. Let me take you back to where this all begins. Not to a garage workshop, not to a restoration hobbyist's channel, but to the laboratory of one of the most consequential scientists in the history of physics in London in the early 19th century. Michael Faraday was the son of a blacksmith, largely self-educated and by the 1820s the most gifted experimental scientist in England. His investigations into the relationship between electricity and chemistry produced the foundational laws of electrochemistry that every battery, every electroplating operation, and every electrolytic industrial process in the world still runs on today. Faraday's laws of electrolysis, published in 1833 and 1834, described with mathematical precision how electrical current drives chemical reactions at the surfaces of electrodes submerged in a conducting solution, how metal deposits, how metal dissolves, how chemical compounds are broken down and reformed by the controlled application of electrical potential. Faraday was describing, in the abstract language of physics, exactly the same process that causes iron to rust. Rust forms when iron loses electrons to oxygen in the presence of moisture. The iron atom is oxidized, gaining a positive charge, and combines with oxygen to form the flaky red compound that weakens and eventually destroys the metal. Electrolysis runs this process in reverse. Apply a negative electrical charge to a rusted iron surface submerged in an electrolyte solution, and the iron oxide is reduced. The oxygen is driven out of the compound, electrons are restored to the iron atoms, and the rust converts back to metallic iron at the surface of the part. The process removes no base metal, it removes only the oxide. The tool that emerges from the electrolytic bath is not thinner, not abraded, not scratched. It is simply clean. Museum conservators working with iron artifacts understood this principle and began applying it systematically in the late 19th century. The challenge of conserving ancient iron, Roman nails, Viking swords, medieval agricultural tools recovered from waterlogged archaeological sites, was that conventional cleaning methods were invariably destructive. Wire brushing removed surface detail along with surface corrosion. Chemical rust removers attacked the base metal. Abrasive blasting destroyed the patina that carried evidence of manufacturing methods in use. Electrolysis offered something no mechanical or chemical method could provide, a cleaning process that was selective for iron oxide and inert toward metallic iron. The corrosion came off. The metal beneath it was preserved exactly as it was before the cleaning began. By the 1920s, electrolytic cleaning was standard practice in the conservation departments of major museums across Europe and North America. The British Museum, the Smithsonian, the Louvre, Every institution with significant iron collections was using electrolysis to clean and stabilize corroded artifacts that would have been unrestorable by any other method. The technique was documented in conservation literature, taught in museum studies programs, and refined by decades of professional practice into a reliable, reproducible process. And then it stopped at the museum door. It never migrated to the hardware store. It never appeared in tool care guides. It never made it onto the pages of the woodworking and machinist magazines that shape what home shop owners know about caring for their equipment. The knowledge existed in a professional conservation context and nowhere else in the consumer information environment for the entire 20th century. Not because the technique was too complex for home use. The basic setup requires a plastic container, water, washing soda, a battery charger, and a piece of scrap steel, but because no commercial interest existed to communicate it. Conservation knowledge lives in conservation literature. Tool replacement revenue lives in hardware stores. The two never needed to meet. Now let me show you exactly how electrolysis removes rust at the molecular level, because the chemistry is one of the most satisfying stories in applied physics, and understanding it will make you permanently confident about restoring metal that everyone else has written off. Iron rusts through oxidation. An iron atom at the surface of the metal loses electrons to the surrounding environment and becomes a positively charged iron ion that combines with oxygen to form iron oxide. Rust is not a protective coating. It is an ongoing reaction that progresses inward through the metal until there is no metal left. Electrolysis reverses this by supplying the electrons that the iron ions lost. When a rusted iron part is connected to the negative terminal of a DC power source and submerged in an electrolyte solution, electrons flow from the power source into the iron oxide at the surface. The iron ions in the oxide receive these electrons and are reduced back to metallic iron. The oxygen is released into the solution and migrates toward the positive electrode. The process is selective in a way that no abrasive or chemical rust remover can replicate. The reduction reaction occurs specifically at the iron oxide surface because that is where the conducting path between the electrolyte and the base metal exists. Metallic iron, which has a different electrical potential than iron oxide, does not participate in the reduction reaction. The rust is removed. The metal is not touched. The electrolyte solution provides the ionic conductivity that completes the electrical circuit. The ideal electrolyte for rust removal is washing soda dissolved in water, a mildly alkaline solution with sufficient conductivity for efficient rust removal at low voltage without the aggressive chemistry that would damage paint, wood handles, or non-ferrous components that might be present on the tool being cleaned. A study published in the journal Studies in Conservation in 1998 compared electrolytic rust removal against 5 other conservation methods across 20 replicate iron coupons corroded to standardized severity. Electrolysis showed the highest surface preservation score of any method tested, removing rust completely while retaining the highest percentage of original surface topography and base metal dimensions. For a woodworking plane with machined surfaces, a cast iron skillet with manufacturer's markings, or a vintage hand tool with filing marks that represent part of the object's functional character, this matters enormously. The surface that emerges from electrolysis is the surface the tool was made with, uncovered and preserved rather than abraded and diminished. Now here's where the story becomes very uncomfortable for the tool replacement market. Every box of rust remover gel sold at a hardware store, every bottle of navel jelly, every electrolytic rust remover kit marketed at $60 to $120 as a specialized tool restoration product is extracting value from the same information asymmetry. The active chemistry in commercial rust remover gel is phosphoric acid, which converts iron oxide to iron phosphate, a more stable but still nonmetallic compound that requires subsequent priming to prevent recurrence. It leaves a gray residue, removes some base metal along with the oxide, and works incompletely on deep incrustation. The commercial electrolytic rust remover kit contains a plastic tank, a power supply, and a solution packet, materials that cost $3 to $4 to source individually, sold in branded packaging for $60 to $120. The hand tool market benefits directly from this asymmetry. Vintage tools, the cast iron planes, the brace and bit sets, the draw knives and cabinet scrapers manufactured to higher standards and from better steel than most modern equivalents, are sold at estate sales and flea markets at prices that reflect their rusted condition. The price difference between a rusted tool and a restored equivalent can be 5 to 20 times. That gap exists almost entirely because of an information gap. The people who know how to restore tools buy cheap. The people who do not know throw away or sell cheap. And the tool manufacturers who benefit from replacement sales have never had a reason to close the gap. Here is exactly what to do. This is the part that costs $1 and works better than anything the restoration product market has ever sold. You will need a plastic container large enough to fully submerge the tool, a plastic storage bin, a large bucket, or plastic storage tote. You will need washing soda, sodium carbonate, from the laundry aisle, approximately 1 tablespoon per gallon of water. You will need a battery charger capable of producing 6 to 12 volts DC at 1 to 10 amps. Any automotive battery charger works. You will need a piece of scrap steel to serve as the sacrificial anode, a length of rebar, a piece of angle iron, any steel you do not mind sacrificing, and you will need wire or alligator clip leads to make the electrical connections. Fill your container with enough water to fully submerge the item. Dissolve 1 tablespoon of washing soda per gallon of water. Suspend the rusted item in the solution without allowing it to touch the container walls or the anode. Connect the negative terminal of your battery charger to the rusted item. This is the cathode connection and the critical one. Connect the positive terminal to your sacrificial anode steel, positioned parallel to the item and separated by several inches. The anode and the item must not touch. Set the charger to its lowest amperage setting, typically 2 amps. You should immediately see bubbling at both the item and the anode. Fine bubbles of hydrogen gas at the item and oxygen gas at the anode. The solution will gradually turn orange-brown as iron oxide is released from the item into the electrolyte. This is the rust leaving the metal. Allow the process to run for 8 to 24 hours, depending on the severity of the rust. When the visible rust has been converted, remove the item and rinse it immediately with clean water. Dry it completely as quickly as possible. The clean metal surface is more reactive than the original oxidized surface and will begin to flash rust within minutes if left wet. A quick pass with a hairdryer removes surface moisture effectively. Apply a protective oil immediately after drying. For cast iron cookware, the electrolytic process produces a completely clean surface ideal for reseasoning. After drying and oiling, place the cleaned skillet in an oven at 450 degrees for 1 hour, upside down, with foil below to catch oil drips. Repeat 3 times. The result is a cast iron surface that is, in the assessment of every experienced cast iron cook who has restored vintage pieces this way, superior to any new cast iron product currently manufactured. The old iron is finer grained, smoother, and better suited to developing a durable seasoning than the rough sand-cast surface of new mass-market cast iron. A machinist in Ohio documented the electrolytic restoration of a complete set of Stanley hand planes, 14 planes in total, purchased from an estate sale in completely rusted, apparently unusable condition for $42. After electrolytic cleaning, sharpening, and minor adjustment, the complete set was valued at over $800 in restored condition. Total restoration cost, including electricity, washing soda, and sharpening supplies, was less than $20. The information that made the difference between $42 of rust and $800 of functional precision tools was available to anyone who knew to look for it. Almost no one does. The plastic bin is already in your garage. The battery charger is already on your shelf. The washing soda is already in the laundry aisle. The rusted tool is already waiting. Now you know what to do with all 4 of them. If this vault changed how you look at every piece of rusted metal you have ever considered throwing away, subscribe and share this now. Every share keeps $1 Miracle digging in the places the tool industry hoped we would never look. The next vault opens soon, and what is inside has been generating billions in replacement revenue from a problem that a plastic bin and $2 of washing soda solves permanently.